that the Z in is fairly straightforward. The Z out is still a voltage divider, and he says to keep the amplitude. So you set up your voltage divider, your emitter follower. After you do Z in, you put in some big resistor. Maybe it's 330. It depends. If your beta is about 100, then 330 would be the answer. Would be the right resistor. Now for Z out, it's not quite as straightforward. So we put the 33K back in. He says keep the voltage low for V7. I don't see where it's that big of a deal, but you should write it down because we're looking at the output before and after the load. Now, could we put two oscilloscope probes there? That's a good question. Maybe. I don't know why not, but he makes it sound like we can't. So you might try it. But he's very unclear on how to do this. It took me a long time to figure it out. So you could attempt to do a. Oh, right. The whole point of you can't do this because you want to know what V-Thevenin is, and the V-Thevenin is the unloaded, right? So you have to measure V out here. He says to keep the amplitude about 1 volt. I don't see any special reason to do that, but I don't see any special reason not to do it. So now we've set up this new voltage divider down here, and we know we have a V-Thevenin, so that's the unloaded circuit, and we measure V-Thevenin, and so that would be our V amplitude. And I would guess as long as it's 1 to 2 volts, it's fine, because with a 12-volt supply, you should easily be able to track up to 10 volts, right? So I don't quite understand why he says that. And now when we add the load, the capacitor doesn't come into play because of the RC constant. You have to, I think he recommends a frequency range. At 4.7 microfarads and 1K, that's a pretty large time constant. So I think if you're about 1,000 hertz at most, you should be fine. But you can just look and see if there's a phase shift, right? That's all. You can look at V out, look at the V here and the V there, and if there's a phase shift, then you know you've got the frequency wrong. So anyways, now when we measure V out, we have this voltage divider, the Z out that we don't know, and we have our Z of our load, and we know that the V out over the V-Thevenin is going to be this, right? That's not a mystery. So then you need to extract Z out, and it's a common technique to just, so you don't have to write this over and over again, you just call it A. And I didn't do all the steps here, but you go through the algebra here, and you end up with Z out here. So R load minus AR load over A. But you should do the algebra and double check it. So you start out with A equals to R load over Z out plus R load. And you know that cartoon, a miracle occurs. It's like, I think you better be a little more clear in this step, Quimby. It's a Far Side cartoon. And you end up with R load minus A times R load over A. So I want to see you do this algebra. I want to see algebra. And he says, then you can infer beta, except that he just gives you no clue how to infer beta. I mean, he gives a clue, but it's not very easy to understand. So what you do is you do a little ansatz where you say, okay, I'm just going to act as if the transistor doesn't exist. And I have a voltage divider, which is the R base and the R emitter. And I know that the Z out of a voltage divider like this would be this combination right here, because I just do R base in parallel with RE. And if you do that, you end up with a value, in my case, with idealistic numbers, of an R base equal to 0.33K. So perhaps I should have put primes on it all the way through, but I didn't bother. So I end up solving for R base, and I end up with 0.33K, but I say, oh, wait a minute, though. It's actually 33K. And now you see your beta again. In my case, 100. It's not easy. It's not, this is a lot of work, and I don't see how in the world you are supposed to figure that out. It took me a long time to figure it out. And I'll post these slides at some point. Now, another thing I wanted to show you is it tells you to wire up the common emitter amp, and it tells you to predict the gain. And it's like, I don't know how in the world he thinks that you're going to do that. So I'm going to do it for you. Oops. Come on. Where'd it go? All right, there it is. All right. Does anybody need me to go back one or two? That one, yeah. I'll pause this a moment. All right, let's start again here. So what I had said is that if I wiggle at V base, that the changes in the base voltage are going to equal the changes in the emitter voltage, even though there's a voltage drop, a DC voltage drop from the base to the emitter, that the wiggles will always be equal. Now, we can calculate the current at the emitter, which we are going to, in the very simplistic model, ignoring beta, we're going to say these two currents are the same. And in fact, I thought they always are the same. Well, it doesn't matter right now. Oh, yeah. So it turns out I emitter is equal to strictly speaking, I emitter is equal to I C plus beta I base or something like that. No, I don't remember. Yeah, I base, yeah. But I base is so tiny we can ignore it. And when it comes to wiggles, of course, we can completely ignore it. But in any event, we determine IE by taking the voltage at the emitter and dividing by the resistance at the emitter. So if that's true, then the wiggles in the current, I current, are equal to the wiggles in the base divided by the resistance of the emitter, at the emitter resistor. RC has no effect on IC. That's tough it's a little tough sometimes to work with that. So V out is the wiggles in V out are going to equal to the wiggles in IC times RC. Because we know in the DC sense, V out here is simply going to equal the voltage drop across this resistor. And so it would be a function, we would have to know what V plus is. But when it comes to wiggles, we don't care about what V plus is. It's just the changes in the current. So notice that V in is and V base are basically the same thing. So then I can rearrange this equation, delta V in equals delta IC times R emitter. And then we have our classic, we want to know what goes on. V out over V in, but now it's delta V out over V in equals delta IC RC divided by delta IC RE. And you notice those cancel. So the gain of this amplifier is simply RC over RE. Isn't that interesting? You don't care about what is the V plus. You don't care anything about the transistor. You actually don't even talk about beta. Isn't that something? That's why that's not good strategy to focus on the beta of the transistor like many classes do. In fact, that's how I was taught. And then we had to learn the exceptions when it didn't count. It was just really difficult to do. But it was a different way of understanding things. I'm not criticizing Dr. Coleman. Okay, so if I look at the book, this means that some of us might get to the common emitter amplifier. It's already 5:30. So what I'd like, part of the, for the hand-in, I'd like you for reading assignment, I'd like you to go and look at 5. Oh, I think maybe it's 4. Hold on a minute. Let me just make it absolutely certain. Worked problems. So it's most likely it's 4W, not 5. 4. Yeah. 4W. And it would be 1 and 2. Yep. Try to synopsize. Don't have to write every blessed thing. 4W.1 and 4W.2. I want you to study about biasing. I want you to try to learn about biasing, quiescent currents, and then the effect of biasing, for example, on Z in. So just try to outline what you're reading in those two sections. Don't write a novel, and don't worry if you're not quite sure what you're writing down there. Oh, one hint is that in 4W1, I believe it is. I was just studying it. So in this emitter follower, you're planning to drive this 4.7K load. And later on, he talks about, let's see if I find it. Yeah, here. And it looks a little confusing because see this 4.7K in parallel? And he doesn't even mention that that's our load. And you're pages later, and you're like, where the fuck did that come from? So now you know, and that'll help you when you're doing your notes. Okay? And again, if you don't finish it, don't stress. It's a lot of words, but it ends up being fairly straightforward. He even gives you an example about this cartoon he makes. So see if you can break it down into a list of steps. Here it is. Right there. So this is a given, right? So 2, I choose RE, and then so I in fact use this for a guide. How do I choose RE? And I say, oh, I need the voltage drop to be this, right? And that makes it very short if you do it that way. And then the phase splitter, this is a huge, doing this worked example and understanding each of the steps, you'll learn a lot about transistors, and it'll help you on one of the homework on transistor. It's really, really useful. And I have all kinds of notes I've made. So on Tuesday, we'll talk about these two things, and so you can fill in your blanks. Okay? So we got about, well, we don't have a whole lot of time left. And so I'll stop this one, and I'll get this